In this video, I'll be building another radio from QRPGuys, the Paraset 40. Unfortunately, this kit is discontinued, but I will include a link to the QRPGuys website for those interested. The radio itself was designed by Steve Weber to commemorate the Paraset transceiver, which was developed in World War II and dropped by parachute to Allied resistance groups in France and the Netherlands and so forth. The radio itself is a regenerative receiver design. Regenerative receivers were popular in the 1920s and 30s, and it works by introducing positive feedback back to the input, which results in a very high gain with very few components. Selectivity is achieved with a tuned circuit in the amplifier, and I'll go into a little more detail on that as we walk through the schematic itself. As usual, I'll be building this up module by module, and I've highlighted the modules here on the schematic that I'll be walking through. But let's go into each one of those modules and walk through that. So the first section that we'll be looking at is the transmitter portion. You can see that in the top left of the schematic. When I first looked at this, I couldn't figure out how is the transmitter tuned, and the answer isn't. It operates at a fixed frequency, and it's governed by whichever one of these two crystals is switched into the circuit. So Q5 is the initial amplifier in this oscillator circuit here, and then Q3 and 4 are a pair of BS170s connected in parallel, which form the final amplifier. There's a spot switch here, and the job of that spot switch is it allows the operator to transmit and to hear the signal in the receiver. So this is basically to figure out where in the sort of receiver spectrum you're transmitting. So these FETs here, Q6, Q2, Q1, and then down here at Q8 are all part of the transmit-receive circuitry, and they sort of pull in the receiver and the transmitter in and out of the received signal path. We have up here diode D3. That's used to protect the final amplifier in the event that you have a poor SWR condition. So straight after the transmitter portion, you have the low-pass filter here, obviously to operate to give you that sort of spectrally pure signal. This will be heavy in harmonics coming out of here, and this low-pass filter will get rid of all that. Up to the top right, we have the sidetone generator, and the job of the sidetone generator is to simply emit a tone it's an oscillator circuit, and it emits a roughly 600 hertz tone out through the headphone jack on transmit. So moving to the kind of the heart of the receiver itself, so we have the regen receiver down the bottom left here, and that consists of two main components. So we've got the regen receiver here, and then we've got the audio amplifier off to the right-hand side. As I mentioned before, the regenerative receiver consists of an input tuned circuit, which consists of this inductor here on T1, and then these capacitors here, and we've got 1N4W1 configured as a varactor, which I'll talk about a bit later. So here's the tuned circuit here. And then we have an amplifier here at Q11, which has its positive feedback coming back through here to this winding on T1. So there's the positive feedback coming through here. This winding is actually called, typically it's called the tickler. And one of the challenges with regenerative receivers is you can actually get it radiating if you're not careful. So this frequency is acting at the receive frequency. So if you're not careful, you can actually end up transmitting that received frequency out through the antenna. And the job of this transistor here, Q7, is to isolate the antenna from the regenerative section. Just a final note on the regenerative receiver portion. Fine-tuning is accomplished with this part of the circuit here, and what that does is basically adjust a reverse bias voltage on D6 here. It's a 1N4W1 diode, and this actually acts as a varactor, which adds or subtracts capacitance from the tuned circuit, thus changing the frequency of the tuned circuit. So straight after the regenerative receiver, we have the audio amplifier and filtering. And basically, the signal that's coming out of here is actually a beat frequency, which is the difference between the received RF and the frequency of oscillation of this portion of the circuit here, the regenerative detector. So you'll get an audio signal coming out here, and the first thing that is done is it passes through this low-pass audio filter here. I'm not sure what frequency this low-pass audio filter is running at. I'll have to do some calcs here, but you've got this sort of typical pi structure here with a 4.7K resistor. You've got a pair of 0.001 microfarad capacitors. I'll figure out what that is. It's probably going to be around 1 kilohertz or so, given this is a CW receiver. Then we have some more amplification here through this sort of Darlington configuration of Q12 and Q9. It then passes through this volume control for some further attenuation if required, and then finally out through this buffer at Q13 here. Now, one thing to note is jack J4 is actually at the supply voltage, so we'll have to be a little bit careful when we're kind of connecting this up to make sure that both of these are at the supply voltage. So we have to be careful not to ground either side of that jack. Moving on quickly to the order of construction. So what I'll probably do here is start with the Sidetone generator. That's a nice isolated piece of the circuit. We'll be able to sort of test the oscillation frequency there, see how close it is to that guess of 600 hertz that I said before. I actually simulated this in LT Spice to see, and it was oscillating around about 600 hertz. We'll then move on to the low-pass filter. We'll be able to construct that separately. We'll be able to, and what I'll do is I'll put this on the spectrum analyzer, and we'll see what frequencies it's actually operating at. Then moving back further in the circuit, we'll then pull together the transmitter portion. Like I said, it's completely isolated from the receiver side, so there's no local oscillator or anything in this circuit here. So that'll be easy to pull together. Then we'll move to the audio amplifier. We'll pull that together. I'll be able to inject an audio signal right here, and we'll be able to confirm that this is working fine. And then finally, moving back to the regenerative receiver, we'll pull this together. Obviously, we've got a nice, interesting transformer in T1 here with multiple windings as part of the construction. So that'll be a bit of fun to pull together. Now, this is obviously the tricky. You got to get the order of the windings right, or you'll get negative feedback on the transformer rather than positive. So anyway, that's what I plan to do. I'll probably break this video into a couple of parts. I think I'll probably do this portion in the first video, following up with the remainder in a follow-up video. Otherwise, the video tends to get a bit long. So anyway, what I'll do is I'll first get this Sidetone generator installed, and we'll do some testing. Okay, so I'm about ready to get started with the Sidetone generator. The transistor, the 2N3904, which is the heart of the Sidetone oscillators right here. It's obviously surrounded by a pile of resistors and capacitors that form the oscillator itself. And then I'll also have to obviously include the power jack and the key jack. And let me just sort of pan down to the schematic here. So here's the key jack here. I'll have to include this resistor here also. And this is grounded on key press, which actually turns this oscillator on here. When the key is released, you actually get supply voltage appearing here, which turns the oscillator off. So anyway, let's get on with that. Get that on the circuit, and then we'll be ready to do some testing. Okay, so the Sidetone generator's pulled together, as you can see here. I'm actually probing at the output of the oscillator here, so let's just pan down to the circuit so I can show you where I'm probing. So this capacitor here that is unpopulated, and I'm probing right here. Just some other notes. I mean, obviously this is the supply circuitry here, so I had to get that installed. Reverse protection diode, there's a little filtering cap here. And then let's just pan up so you can see I've got a key switch here, sort of a fake key switch here. This thing here, the red and the black together is key down. And let's have a look at the output on the oscilloscope here so you can see that. The light's a bit in the way, so let me move that out of the way. So I'm just, this is simulating a key press down, and there you can see there's the output from the oscillator, and it is indeed around about 600 hertz. That's what the kind of simulation told me I would get as well. So, and a pretty strong signal too. So, you know, obviously this is into high impedance, but it's 6.8 volts peak-to-peak signal at 608 hertz. So we're ready to move on to the next stage of the build, which is the low-pass filter. So here's the low-pass filter here, a pair of T37-2s with 20 windings on it, on each one. Some attendant caps here, a couple of 330 picofarad, a 680 picofarad. I'll have to check what the value of this is. That might be for the 80 meter version of the kit, and then a 68 picofarad across this L2 here. And then there's a B and C connector. So what I'll do is pull this together, and then I'll do the usual thing, inject a signal into here and with the spectrum analyzer, and we'll see what the shape of the filter is. Okay, so as you can see, the low-pass filter is installed. Indeed, capacitor C2B was unpopulated. You can see I'm injecting the signal. This is coming from the spectrum analyzer, the tracking generator, the spectrum analyzer, into this point on C8. Yellow is grounded off at C4 there. There's the two T37-2s and the associated caps. And then I'm pulling off the signal out of the antenna, and it's going to the spectrum analyzer. So there we go. There you can see there's that classic low-pass filter shape there. If I turn the markers on, bear with me, I've just got to pull this back a bit. So just looking at where that, so the tracking generator is injecting a minus 20 dB signal. So looking for the 3 dB point, it is around 7.7 megahertz, which is this 40 meter transmitter. So that's perfect. So what I'll do now is move back again in the transmitter path and include the PA and the transmitter itself. So that will be coming right up. Okay, so just quickly through the transmitter section. So basically I'll be building up all this part here. Now the kit only comes with one crystal, so it's a 7.030 megahertz crystal. So I'll just include, I'll just put in one of those. It didn't come with this switch, so I'll just bridge that out and fix it to 7.030. The rest of it's pretty straightforward, as you can see here. I will be installing Q1 and Q2, which is involved in the transmit-receive circuitry. And then there's just this toroid to wind here, which is on a T3743A. I think that's what it's on. But it's 8 turns on that, so that's pretty simple. We have this Xena here, which is, I think, a 47-volt Xena, which, as I mentioned earlier, is involved in protecting the finals if you have a poor SWR condition, such as the antenna is not connected, for example. So anyway, I'll pull this together, and then after that, we'll be in a position to actually test the transmitter output. Okay, so this is just a quick build update, and just to describe, I've installed everything up to the BS170s and the inductor here. So all this is installed, so I can actually do some probing around, testing to see. So what I'm going to do is I'm going to probe right here at the gate of the BS170s, or at least where the BS170s go. Let's pan up to the oscilloscope so you can see that. All right, I'll transmit. There we go. There's the waveform at the gate of the BS170s, and you can see the output frequency is 7.02975 megahertz, which is obviously very close to the 7.030 frequency of the crystal. So what I'll do is I'll move on. I'll put in the BS170s. Just moving this over a little bit so you can see it. So I've got these two BS170s here, this inductor here, diode, this cap here, and then we'll be ready to test the output through the low-pass filter. That's coming right up. Okay, so I've got those BS170s installed. Unfortunately, we are getting far from a clean output from this. As you can see, there is that 7 megahertz signal is in there, but it's there's a lot of other waveforms in there. It's almost like the the amplifier is oscillating or something. I'm going to have to do some digging and kind of see what's what. So I'll take you through that, and we'll see where we go. Okay, so let me move back in the transmit chain, and now I'm probing at the gate of the BS170s. Let's see what the waveform looks like. So you can see there's that distortion there too. So well, that's interesting. So there's a reasonable signal there. But as you can see, it is greatly distorted there. So that's probing at the gate of the BS170s, and obviously there's a problem right there. It doesn't really narrow it down. The problem could be with the kind of oscillator section, or it could be a bad BS170. What I might do is I'll pop out one of those BS170s and we'll see if anything changes. Okay, so I've popped both of those BS170s out, and again probing at the gate of where the BS170s are. Bear with me here for a moment. And as you can see, I mean, it's obviously not a pure sine wave, but there's no hint of that sort of oscillation in there. So maybe I have a bad BS170 in the pair. So what I'll do is I'll replace one of the BS170s with some of the a BS170 that I have in stock, and then we'll retest. Okay, so I've replaced one of the BS170s. So again, probing at the gate just to check out the signal. The signal still looks good there. I mean, obviously there is some, you can see from this trace, there's something going on in there, but it's by no means as distorted as it was before. So what I'll do now is I'll probe at the antenna and see what I'm getting out of the antenna. All right, so I'm now probing at the antenna. Again, I've only got one of the BS170, so I should expect less power on the output, but let's see that. As you can see, that sine wave is pretty clean there, and even if I increase the time base, I'm not seeing any of that distortion I saw before. So it remains to be seen if I replace the other BS, if I put fill the remaining BS170 slot, will I go back to before. So let me do that. I'll again pull out a BS170 out of stock, and let's try it again. Okay, so I put the remaining, the other BS170 back in, and as you can see, straight away I get the distortion on the output. That's a terrible output, and that's probing at the antenna, so after the low pass filter. So I'm going to have to go away and have a bit of a think about this. Not quite sure. I've kind of double-checked the circuit. It does appear to be working fine. As soon as I add that other BS170, I get this distortion in the output. So let me have a bit of a think about that, and I'll be right back. So just confirming, I've pulled the other BS170 out just to see if it was something wrong with Q4 or Q3 separately. And as you can see, the trace is fine when I have a single BS170 in there. And I get all that distortion if I have both BS170s in Q3 and Q4. So I'm going to continue probing around, and we'll see what we see. Well, it's even more of a mystery now. I replaced that BS170 with another BS170. Now I've got both BS170s populated, and it's all working fine now, so I'm not quite sure what's going on here. I can't believe I had, let me just check the frequency there, should be 7.02815, well that's close enough I suppose, but yeah, very strange indeed. Let's just go out, see if we've got any strange behavior. No, that's perfect. And 33.6 volts peak to peak, which in a 50 ohm load is, I'll get this wrong. I always get this. I think it's about 2.7 or so watts. So, which is about what we should see here. So anyway, I'm gonna keep playing around with this. But this probably draws to the close of the transmitter portion of the circuit. So just panning down to the circuit, we'll see what we've installed so far. So here's the transmitter section. Here's the low pass filter. There's those two BS170s there. So I was probing right at the antenna output here and getting that 33.6 volt peak to peak at roughly 7.028 megahertz. So the one final thing probably to test is to make sure that Sidetone generator is actually working too. So I'll do that. I do have a few things to install to get that appearing on the headphone. So I'll go away and do that, come back, and then we'll test the Sidetone generator. Okay, so just a final wrap on this, and I've been continuing to dig to sort of figure out what is going on that produces that distortion. One of the things that I've noticed is the transmitter seems to be very sensitive to the input supply voltage. So here we are at about 15.8 volts, and anything above 15.5 volts seems to be quite reliable. But as I turn the voltage down, so let's turn the voltage down to, let's say we're about 12.5 volts now, you'll see I get that distorted signal. And interestingly, as I raise the supply voltage, we still get the distorted signal up to a point around about 15.7 volts. It kind of snaps into that fine output signal. So I'm not sure what's going on here. Obviously this is a very deep subject, and I'm not quite sure what could be causing this. If anyone has any suggestions, I'd love to hear about maybe suggestions to rectify what's going on in the circuit here. One of the other things also, I've only built up part of the kit here, so it could be relying on kind of the remaining filter caps. Perhaps there's some sort of RF leakage back into the supply or something. I don't really know. Not enough of a, as I've said many times before, I'm more of a hacker than any kind of expert here. So any suggestions on what might be going on? Very interested to hear that. What I'll do is I'll wrap part one now, and then in part two of this, I'll build up the receiver, and then we'll take it from there. So I hope you enjoyed this video. More to come.